Hello, this video came about because some months ago, MC put out a challenge to flat earthers offering $10,000 worth of Bitcoin to any flat earther who could successfully determine the geolocation of a marine sextant challenge and show how they could derive that location using flat earth math, or more specifically, how they could derive a geolocation from the values provided using anything other than globe earth math. And at the time, I had started working on a marine sextant challenge solving bit of code in my skywatching app. At the time, I didn't get it working the way I wanted it to work, so I put it aside. And recently, there was one flat earther who challenged Ruhif. As it turns out, Ruhif went first, and all that was left was the flat earther to say, I agree with everything you said, but you ended up using flat earth geometry and flat earth observations, etc. So I decided I was going to go back to my skywatching app and take another look to see if I could somehow fix what I had done wrong in the code. And I got something that was extremely close. And fast forward a couple of weeks, and now I am presenting this video here. So it doesn't really matter how you derive an altitude angle. It can be using a sextant to get measurement readings from a reflecting pool. It can be measuring the angle from the horizon to the star. It can be using the inclination that your cell phone provides. And the cell phone works entirely by gravity, and all of these measurements end up agreeing to within a margin of error in terms of the measured altitude. So it doesn't really matter exactly how these angles are derived. And this is one of those things where the flat earthers argue endlessly over the measurement of the angles, and it's almost like they are too afraid to use the values that are provided in order to get to the end point of the exercise, which is to derive your geolocation using those observations. So I put a little bit of a teaser video a couple of weeks ago saying that I am able to estimate a geolocation that matches the expected geolocation exclusively using math. So I do not need lookup tables in an almanac. I do not need to use the derivations that somebody else has done. I can use a set of predetermined equations to arrive at this value. So that's really what this video is about. And I could let others peek under the hood and see the code that I wrote for this. And it's really a bit of a mess, and I don't really want to show the code. But what I did last weekend was I did something that was just as good. I did a very, very quick mock-up web page that should work in any browser. And I'm going to make this web page available. So check the description below. There should be a link to my GitHub project area thing, whatever it's called, and you should get a copy of this HTML file. And I only spent the better part of a couple of days over last weekend and a couple of evenings earlier this past week to write this, so it may not be pretty, but it does get the job done. I've included several samples so that you can see how it works. This one is the example given when MC Toon, failing to get flat earthers to submit their answer to his challenge, he then put out another challenge for the globe earth, and I think he got a correct answer in 20 minutes, I think. These are the values that were used in that challenge. Ruhif was given a choice of two sample problems, and I believe he picked number 2, but he was also given 1 as well. And Ruhif has since put on his community tab of his channel both challenges. So I just ended up using that to fill these 2 in. And I've also created 2 random observation challenges as well. You can pick whether you want to use globe earth math or whether you want to use flat Earth math. If you look at the source code of this page, at the very top you're going to see a list of, I think it's the 600 brightest stars, I think. The ones that we've bothered naming, like Bellatrix or Pollux or Peacock or etc. Then below that you're going to see a section of globe Earth based functions. These three functions are various derivations of the Haversine function that, for example, given one geolocation, a distance, and a bearing, it will calculate the other geolocation, or given two geolocations, it can calculate a great circle route distance, or it can also calculate the bearing. I believe there's a distinction between traveling in a straight line that follows a great circle route versus going in a straight line where the compass needle stays oriented the same way, and the two are not the same. So I might have this name wrong. This is also globe Earth based, which is given a right ascension and a declination and your geolocation, it will calculate the altitude and azimuth for that object. So based on where you are and the right ascension and declination, it will transform that into an altitude and azimuth. Then we have the flat Earth functions here, which are strictly planar geometry based. These sets of methods are what all of the other ones below call, and based on the model that you have selected, it will call the one or the other to calculate the appropriate thing. This will calculate the right ascension, declination, and the ground position of a star. This is tied to the elements in the web page so that it will find the appropriate time, date, time zone, and star, and it will calculate the appropriate entries. And I'm not going to go through the rest of this code. It should be pretty much self-explanatory, but when you enter all these values in, it will make all the appropriate calculations, and it will output into each of these sections the math that it has done in order to derive those geolocations. So given the celestial coordinate of a given star and the observation time and date, along with the observer's geolocation, which is less necessary to calculate the ground position, but it is required to calculate the angle to the star. Once it's done all of this, it will arrive at a final latitude and longitude on the Earth, which corresponds to the ground position for the star at that time. So it does this for all three stars. It's the same math, it's the same set of computations. The only thing that changes are the inputs, which are these. Next, given an observer height, an index error, and the various measured angles to the stars, it will calculate an expected atmospheric refraction. Then it will subtract each of those corrections from the measured star angle to derive a true altitude for that star. Then transforming it to the zenith angle, it then calculates 69 miles, 60 nautical miles, or 111.19 kilometers per degree, to calculate the distance that one must travel from where they are to the GP of where the star happens to be at that point. So this is how I go about calculating the distance to the GP for each of those stars. And the final bit is something that I'm still working on because I'm not quite satisfied with the precision that I can get out of it. If we switch to the globe Earth math, for example, you can see that rather than being all concentric circles, these circles now deform and they all intersect at one point, which is where that black dot is. And the way I ended up determining the estimated geolocation is based on going through the various combinations of angles to find the closest distance between those 2 points. Starting at the calculated ground position for the first star like Arcturus, the expected distance to the ground position based on the angle measured, and a bearing. So I basically go through all 360 degrees in 1 degree increments. I'm looking for the shortest distance to a similar bearing on each of the other two. And so what I'm looking for is the shortest distance. Once I have that shortest distance, I mark down the bearing and I tighten the resolution from 1 degree to half, a quarter, and I keep dividing the scan resolution by 2 until I get to a certain point, and I keep looking for the bearing that is the shortest distance. And then I do likewise for the second star and likewise for the third star. After the initial bearing discovery, I loop several more times, but I use the last known bearing that was used from the previous loop. When I'm done, I'm left with a bearing for each of those 3 stars. I think I'll try to revisit the way that this code is done to see if I can find a better way and a more reliable way, but it does seem to get the job done. And finally, I've got a button here that you can click that will generate a KML file that you can load directly into Google Earth. What I've also done is here you can see that I've got the ground position of the star Altair. This white line, in fact, there are white lines for all 3 of the stars. All 3 of those stars extend all the way to the point of intersection. And here you can see the estimated observer location is actually outside of this triangle. So that's what I'm saying. It's fairly close, but I still need to work on it. You can also generate what it would look like if it was flat and load that into Google Earth. As you can see, they are not circular. And I've added a few extra controls that will let you generate your own challenges if you want. So for example, I can put in a geolocation of 27 point that many north and minus 57 point that many west, which is going to put you right about there. If you click on the angle discovery mode, you can change the time to right now, for example, and it will derive the geolocation for those stars for the indicated time, reverse apply the various corrections, and put that value in for the measured angle to the star so that if somebody were to solve it using the appropriate values provided, they should reverse all of the calculations that this had just done and hopefully derive the correct geolocation. The sign is reversed. It actually subtracts whatever value you put in. So if you want to go into the future, you have to provide a negative number. If you put a positive number, it actually subtracts that. But you can specify in days 27.346 days, for example. So when you click on this, the time is based on that time. And since these values are in the negative, it can't solve it. So let's pick a slightly different offset. And as you can see, it's derived new values for measured angles to the stars. And the last thing that you might want to do if you wanted to use this tool to put out sample problems for somebody to solve, you could lower the resolution of the measurement by truncating to 3 decimal places, for example. And you want to do that without this being checked, because if this is checked, it will recalculate these values. So this is what I threw together last weekend. So just take note of this disclaimer. Check the description below. You should find a link to where you can get a copy of this. I'm going to put it on my GitHub project area thing somewhere. So as you can see, given a choice between using 2-dimensional math to derive a location on the Earth or using 3-dimensional math to find your position on the Earth, the one that works is the 3-dimensional math. Therefore, the Earth needs to be a globe. That's going to be it for now. Thank you for watching. If you liked the video, I would appreciate the thumbs up, the subscribe, comment below, all that other good stuff. I'm going to see you again in another video soon enough, so bye for now.